So we're going to dig deeper into this idea of approximating the size of the elements. Looking at the effective nuclear charge alone is a good first start, but as I implied at the end of the last video, it doesn't always work directly. There's a little bit more um, specificity that we need to look into in order to tell whether something will be larger or not than something else. And this kind of brings us back to the Bohr model of the atom. Now, I didn't show you, well, actually, I did show you this to some degree when we were determining and coming up with the derivation for the Rydberg-Balmer equation. I show you that the radius was given by a bunch of constants together, right? And it looked something like this, right? Now, all of the stuff here is just a collection of constants, with the ones that I kind of keep out being the atomic number and the principal quantum number square. That's what the radius of an element is from the point of view of the Bohr model of the atom. And if you plug in the actual values for Planck's constant, the permittivity of space, the charge of the electron, and the mass of the electron, you find out that all of those constants together end up being a value of 0.529 angstroms. This is known as the Bohr radius, but it is a constant associated with R. So pretty much what you have is the radius of the atom is given by 0.529 multiplied by the principal quantum number squared divided by the atomic number. But that only works if you have a single electron. If you have more than one electron in an atom, you can't exactly use that formula. That being said, now that we have a method for approximating the effective nuclear charge, instead of plugging in the charge of the nucleus itself, we just plug in the charge that the valence electron gets to see, the effective nuclear charge. And to kind of make the math work out a little better, we also finesse the principal quantum number. Instead of just plugging the value of the principal quantum number of the valence electrons, we modify a little bit. Now, the way this goes is that if you go up to the third energy level, the value of n star or n effective is exactly the same as the value of n itself. But when you go farther than that, like if you get to the fourth energy level, instead of using the value of 4 for n in the Slater approximation of the atomic radius, you will use 3.7. If you go up to 5, the value will now have to be 4.0 for the formula. If you get to 6, it will be 4.2. These are just little, you could call them um, correction constants, if you will, to kind of make the equation work a little better. Needless to say, this equation is very rough. Like, you're not going to get values that are like super identical to the true values, the experimental values. But the one thing that this formula does, which I kind of like, is that it keeps the trend that you see in the periodic table pretty much intact. The values are not exactly the same, but the trend remains intact. And that's where I'm going to use this formula and where I'm going to have you use it. So let's take a look at an example. A typical example that you may see in regular exams in chemistry, standardized exams like the one that the ACS administers at Santa Monica. For instance, I could ask you to arrange the following atoms in increasing order of atomic radius. And typically, people expect you to do this just by looking at the periodic table and use the trend of going from bottom to top and from left to right in terms of what happens to the atomic radius. All right, so we're going to arrange them ultimately in this order. And one thing that we know is that if we look at the periodic table, we have nitrogen to the left of oxygen. Underneath nitrogen, we have phosphorus, and underneath oxygen, we have sulfur. So based on the trend that we already established, the fact that going from right to left, the size is going to increase. And going from top to bottom, the size is also going to increase. What we can say right out of the gate is that, well, if increasing the size of the element allows us to go from right to left and from top to bottom, then oxygen by default has to be the smallest element in this series. And phosphorus by default has to be the largest one, just by following the trend that we learned in the periodic table, right? So oxygen is the smallest, phosphorus is the largest. That we have no problem with. The problem, however, arises with the elements in the middle, nitrogen and sulfur, because on the one hand, nitrogen is farther to the left than oxygen, but it is farther up than phosphorus. And sulfur right here is farther to the right than phosphorus, but it is below nitrogen. So then the question becomes, well, which one is the smaller one? Is nitrogen the smaller one, or is sulfur the smaller one? And I personally used to have a huge problem with this when I was a student. Like, I could never really predict it until I realized Slater's rules is here to help me. And that's what we're going to do. We're going to set up the table to figure out whether nitrogen is smaller than sulfur or if it's the other way around. Okay, and just for the sake of completion, I'm going to apply this to all four atoms to show you that it actually works really well. The trend is going to be present in there. Okay, so like any good old Slater's rule problem, and notice here that I just completely remove the 0.30 because we're not going to be looking at the 1s orbital. If anything, we're going to be looking at the 2s 2p groups for nitrogen and oxygen, and the 3s 3p groups for phosphorus and sulfur. So the first thing you do is you write the electron configuration, and then you group the 2s and 2p's of the same energy level together. So for nitrogen, we'll have 2s 2p 5, and for oxygen, we'll have 2s 2p 6. For phosphorus, we'll have 3s 3p 5 and 3s 3p 6, right? And you can see that the trend sort of remains the same for elements of the same group. All right, now we're going to calculate the effective, the shielding constant for each one of these elements. And you do it once again for the valence electrons, nothing but the valence electrons. So for nitrogen, that's the 2s2p group. Same thing for oxygen. For phosphorus and sulfur, we're talking about the 3s3p group. All right, so for nitrogen, we have 5 electrons in the 2s2p group. So 4 out of the 5 will be shielding the fifth one. And so we multiply 4 by 0.35. And then we have one group to the left with lower energy value, 2 electrons present in it. So the 2 get multiplied by 0.85. That's what the table is telling us over here. And we sum these values together to tell us that 4 times 0.35 plus 2 times 0.85 is equal to 3.10. Now we do the same thing with oxygen. Now we have 6 electrons in the 2s2p group, so 5 out of the 6 will be shielding the sixth one by 0.35 since we're in the same group. And we have a group to the left with a lower energy value with 2 electrons, so 2 can multiply by 0.85. All right, when you multiply the numbers and add them together, you find out that the shielding for oxygen is 3.45. All right, on to phosphorus. We have 5 electrons in the 3s3p, so 4 out of the 5 will be shielding with 0.35. And if we look to the left, we have a group of lower energy value 2. There's 8 electrons, so all 8 of those electrons will be shielding with a constant of 0.85. After that, we have energy value that's even lower than 2. So all the electrons in that group get to shield completely with a value of 1, right? So 2 times 1 to account for the full shielding of those electrons. And notice that we're sticking to the sp column right here because the valence electrons that we're looking at are sp electrons, okay? All right, now multiplying all these numbers together and adding them yields a value of 10.20 for phosphorus. For sulfur, we have 6 electrons in the valence group, so we multiply 5 by 0.35. We have 8 electrons in the group to the left, so we multiply 8 by 0.85. And then we have 2 electrons on the group further to the left, so we multiply 2 times 1. Carry on the multiplication and add the numbers together. You should find out that this equals 10.55. All right, now the moment you have the shielding constant, you have to remember this is just the shielding constant you calculated. It's not the effective nuclear charge. You need to subtract these values from the corresponding atomic numbers. All right, so for nitrogen, the atomic number is 7. For oxygen, the atomic number is 8. Phosphorus, atomic number is 15. And sulfur, the atomic number is 16. So we subtract from each one of these atomic numbers the shielding constant that we just calculated. And when you carry the subtraction, you find out that the effective nuclear charge for nitrogen and oxygen are 3.90 and 4.55. The effective nuclear charge for phosphorus and sulfur are 4.80 and 5.45. Okay, so this looks, kind of legit. Now, by looking at this thing, just the effective nuclear charge, you might be able and willing to say that, oh, okay, nitrogen has a lower effective nuclear charge than sulfur, so sulfur has to be smaller than nitrogen. And if you do that and keep it as this, you probably get the wrong answer. In fact, I'll be honest with you, the example of aluminum and gallium, we got lucky that the effective nuclear charge alone happened to predict the trend that we were seeing. Because what you really need to do is apply the Slater approximation of the Bohr atomic radius to figure out the actual sizes. This is really what you need to do to figure out the atomic radius of an element is going to be smaller than another. So this would actually have to be applied to aluminum and gallium as well in the previous example. Okay, so we're going to apply the same rule here. Now, a few things to keep in mind. We need to plug in the effective nuclear charge, which are the values we just calculated for each of the elements, but we also need to plug in the value of n star. And for n star, we're talking about values that differ from regular n if we go past a value of n equal to 3. But in all the cases here, the last group, the valence group, is a 2s 2p or a 3s 3p. So we never go past energy value 3. So it's going to be exactly the values we see here for the valence electrons. For nitrogen and oxygen, the principal quantum number of the valence electrons is 2. For phosphorus and sulfur, the principal quantum number is 3. So we simply plug in all the values. 0.529 times 2 squared divided by the effective nuclear charge. For nitrogen, that's 3.90. For oxygen, that's 4.55. Now for phosphorus and sulfur, the principal quantum number of the valence electrons is 3, so we need to square 3, and we divide it by the effective nuclear charge of 4.80 for phosphorus and 5.45 for sulfur. Okay, now we carry on the calculations, and we find out that for nitrogen, the value is 0.543 angstroms. Yeah, by the way, when you do these calculations, the values you're going to get will be always in angstroms, which if you need a reminder, that's 10 to the 10 angstroms are present in 1 meter. Now for oxygen, the value is 0.465, and you can see here is that oxygen is indeed smaller than nitrogen, which is kind of what we predicted. If you carry the same calculation for phosphorus, we're looking at 0.992 angstroms, and for sulfur, we're looking at 0.874. And here is the actual answer in terms of size. If you look carefully, you realize, nitrogen is actually smaller than sulfur. And phosphorus is in fact the largest thing in here, and oxygen is in fact the smallest thing in here. So now you have your trend. After oxygen, you need to put nitrogen, and after nitrogen comes sulfur. And you will only get this by not just getting the effective nuclear charge, but also applying the revised version of the Bohr atomic radius. Okay, so with this, we'll stop the video right here, and we'll continue on to the next video.